All right. All right, could you please confirm if you can see the screen with the slides?
Yes, doctor. Can see.
Okay, thank you, thank you. Right, so let's get started. So the first topic will be on introduction to semiconductor materials before we go to the heavier part, right? So this is just a simple illustration to show that this guy is working on part-time basis as a conductor. So then he's called semiconductor, right? Right. So we have discussed yesterday about this partly, and you have given different answers. You know, you mentioned silicon, you mentioned sand, and yes, we have seen the origin of the chips or of the integrated circuits, which essentially are transistors, right? And transistors are made on silicon wafers, and silicon wafers are produced from sand, originally from sand. And to be able to get to silicon wafers before you can start the fabrication processes to produce devices, right? Integrated circuit, solar cells, solid state drive, and whatnot. The silicon dioxide needs to be reduced to silicon. So that means you have to remove the oxygen in the silicon dioxide in the sand, right? You have to remove the silicon, the oxygen in the silicon dioxide. Hold on, many students are joining now. Let me approve. Okay, so yeah, to be able to get silicon wafers, you first have to use the silicon dioxide, which is the sand, and then you have to go through certain processes. We're going to learn that in 487. You need to remove the oxygen from the silicon dioxide in order to produce silicon. And this silicon is not yet ready for the fabrication of devices. Okay. Right. Why is it not ready? Because at the moment you have removed the oxygen from the silicon dioxide, the purity level of the silicon is not yet enough. Purity. Just an introduction to this, yeah. So for your information, if you want to produce integrated circuits to be used in all these chips, you need to use silicon with 9N of purity. Okay, 9N of purity. So anyone knows what is 9N? Any ideas? 9N of purity. What does this mean? If anyone knows? Apa maksud 9N? Oh, sorry. Tukar page pula. So 9N here means the silicon has to be purified up to the level when the purity is equal to 9 times of 9. 9 times of number 9. 99 point. So those are 2. 1, 2, 3, 4, 5, 6, 7. Right, altogether 9 n's, 9 of 9 of 9 of n, 9 of n, or 9 of 9. So this is called 9n of purity. So that means you have to have 9 of 9s, right? 9s of 9s. So 99.99997 more, right? 7 more times. Only at that level, your devices can operate as integrated circuits. So if your processes are not up to the level or the purity is not up to 9 Ns, so you just won't get the transistors to function. Okay, so you're going to learn later on a lot more that every device requires a different level of purity. For example, to put things into perspective, if you're working on ICs, so you need to have at least 9 N of silicon for the transistors to work. On the other hand, if you talk about solar cells, silicon-based solar cells, still originates from silicon wafers, so you only need about 6N. That's 6N for the solar cells to function, to work. So then you can already see what does it take for you to have your transistors to work. So you need to reach 9N or it won't work. Okay. On the other hand, if you work on silicon solar cell, 6N is already sufficient for it to work as a solar cell. Okay. So you're going to learn a lot more later on if you take ZAT387 semiconductor fabrication processes in the next semester, where you're going to learn all the processes involved for you to convert the sand into silicon wafers and then silicon wafers into devices, okay, devices on the silicon wafers. So those will be covered in semiconductor fabrication processes. So in this topic, we're going to cover a few basics. For example, primary type of materials, insulators, conductors, semiconductors, and then we're going to have a little review of the crystal structure. But I won't go through this a lot because you have learned a lot on this already in 307, solid state physics. And we're going to learn about crystallinity of semiconductor materials. And we're going to learn a little bit on impurity and doping. And what are p-type and n-type doping, right? So this is just an introduction to the topic, but we're going to go into more details when we go for another chapters. So solid state materials can be grouped into 3 classes. Generally, the materials can be grouped into 3 classes, which are insulators, semiconductors, and conductors. So those 3 distinct groups, right? So if you look at the below chart, okay, they can be arranged with increasing or the change of resistivity, so that is one, and then change of conductivity on the x-axis, right? So you can see, for example, if you want to see the materials in terms of resistivity, you can see it ranges from 10 to the 18 ohm cm to the left up to 10 to the minus 8 now to the right, in terms of resistivity. And then if you invert the resistivity, you can get conductivity, which is in Siemens per centimeter. You can also get the inverse value of this, which is 10 to the minus 18 on the left for conductivity, up to 10 to the 8 Siemens per centimeter on the right. Okay. So now let's look at all the 3 classes: insulators, semiconductors, and conductors. So if you talk about insulators on the far left, so it's obvious that the resistivity is very high. The resistivity is very high in the range of, you can see here, 10 to the 8 up to 10 to the 18 ohm cm. And then if you invert that, the conductivity is very, very small, from 10 to the minus 18 to 10 to the minus 10, right? 0.000 many zeros up to that level. And then the example of materials which are insulators, fused quartz, diamond quartz, glass, nickel oxide, and many more, sulfur, right? So if you look on the far right, on the other hand, if you look on the far right, we can see conductors. So examples are silver, copper, aluminium, platinum, and more metals. And you can see that the resistivity is very, very low on the far right. So it ranges from 10 to the minus 8 up to 10 to the minus 3, somewhere there, 10 to the minus 3. Okay. On the other hand, you can also see the conductivity ranges from 10 to the 3 up to 10 to the 8, pretty much, right? Oops, sorry. So, and the examples of materials are very clear. they are the typical metals that we use. Perhaps some of you are working on metals for whatever purpose for your FYP as well. In the middle, so this is the group that we are very interested in, which is semiconductors. And you can see that the resistivity is in between 10 to the 8 down to 10 to the minus 2, minus 3. And then the conductivity is the inverse. And then there are many examples of semiconductor materials. So they range from elementary semiconductors like silicon, germanium, just one element, right? The silicon. And then you can also have binary like gallium arsenide, gallium phosphide, cadmium sulfide. Can you give another examples of semiconductors? Whether they are elementary or binary or ternary or quaternary. Anyone? Can you give any examples of semiconductor materials? Perhaps those that you are working on at this point in your FYP, or some other materials that you know that belong to semiconductor group. Anyone? Okay, Fatul, perovskite. Yes, perovskite is another material which belongs to semiconductor. Perovskite is one. Okay, any other? Anyone else working on semiconductor materials for your FYP of any sort? Edgar, how about this? How about Sofiyuddin? Sofiyuddin, any other examples? Right, page one, indium nitrate. All right, indium nitrite, you mean? INN, right? INN. Indium nitrite. Indium nitrite, yes. Indium nitrite. INN, indium nitrite. Okay, any other? Sofiyuddin, any examples? Zinc oxide, yes. Zinc oxide. Yes, gas. Good. Aluminium, gallium, arsenide. We normally call that gas. Lagi? Ada lagi? Shasha, thank you. Any other? Lead sulfide. Yes, lead sulfide. Good. Banyak, ah. See, you can see now we have many more, right? Binary, elementary. So you've got ternary as well. Ternary, gas, aluminium, gallium, arsenide. Lagi? Ada lagi? You can write down. You can unmute yourself. Magnesium oxide. Magnesium oxide. I'm not sure. I don't think so. You can check. You try Google and you can share here. I don't think so. Magnesium fluoride, yes, but it's an oxide. I think it's more of insulator, oxide insulator. You can help check. Siapa tadi? Sofiyuddin, right? You can help check online. You will confirm boleh lah. Indium gallium nitride, yes, InGaN, indium gallium nitride, graphene, okay, graphene, right? There will be properties within the spectrum, right? So there are many more materials, right? There are many more materials. Cadmium telluride, copper, indium, gallium selenide, copper, zinc, tin sulfide. What else? Magnesium fluoride. Banyak lah, banyak. So it has a lot of different materials depending on what you are looking for, right? You can go for elementary, you can go for binary, you can go for ternary, you can go for quaternary. Macam-macam. You can go with different combinations, right? So it's good. So in essence, the resistivity and the conductivity of the semiconductor stays in between insulators and conductors. Right. So let's go through the explanation a little bit. Insulators such as fused quartz and glass have very low conductivities, right? Resistivity is the inverse of conductivity, on the order of 10 minus 18 to 10 minus 8 Siemens per cm, just like what you saw on the charts now. Conductors, on the other hand, like silver, aluminum, copper, have very high conductivities, typically in the range of 10 to the 4, 10 to the 6 Siemens per cm. Semiconductors have conductivities in between, just like what we discussed in our first class, right? Conductivities in between insulators and conductors. Semiconductors are sensitive to temperature, so you can actually alter the conductivities of the semiconductor materials by changing many different parameters. For example, You can change the temperature, or you can change the illumination level. You can change the magnetic field around it. You can change the impurity atoms like doping, right, to make them more appealing for electronic applications. So you can when you pick your semiconductor materials, you can already pick based on its original conductivity, and not only that, you are also able to change, to alter the conductivities by different parameters as mentioned, okay, in order to achieve certain specifications or certain properties in your desired applications. Okay, so now let's have a look at insulators. Insulators are very resistive. Resistivity is in the range of 10 to the 10, 10 to the 18 ohm cm. Very high, 10 to the 10, 10 to the 18 ohm cm. Includes glass, plastic, rubber, silicon dioxide, silicon nitride, many other material. Wood, okay, banyak penebat yang you can probably think of. So materials have tightly bound electrons, usually 8 valence electrons in the outer shell, so that make them difficult to move around, even with high voltage applied. So in the typical condition, they are tightly bounded in the outer shell, so they couldn't move, and therefore they couldn't conduct electricity. So to be able to break the connection, you really need a very, very high voltage or high excitation in order to break them and let them free from the bond. Okay, so you can see here, we're going to go through later on the concept of band gap, but I believe you've learned a little bit last time, perhaps. So the typical band gap of insulators are in the region of 5 or above. Okay, so this is the energy gap, the difference between the valence band H and the conduction band H, right? Hujung valence band up to hujung conduction band. So the gap there is called forbidden gap or energy gap, right? Energy gap. And for insulators, it's typically around 5 and bigger, right? So on the other hand, if you look at conductors, they are very conductive, and therefore they're called conductors. Resistivity in the range of 10 minus 4 to 10 minus 6 ohm cm, right? In the minus region, 10 to the minus 4, 10 to the minus 6, typically. And they include metals, for example, gold, silver, aluminium. Typically, they are inclusive of heavily doped semiconductors as well. So, yang paling straightforward ialah when you use metals, they are conductors. But if you use semiconductors, they can also behave like conductors if they are heavily doped, right? So to relate to doping yesterday, we're gonna cover this one in detail later on anyway. So this is where you incorporate impurities such as impurities from group 3 like boron, aluminium, gallium into silicon, for example, as host atoms. Or you can also include impurities from group 5, phosphorus, aluminium, antimony, not aluminium, phosphorus, arsenic, antimony from group 5 into silicon. And not only you include them a lot, right? Until they are called heavily doped. So we're going to learn about this heavily doped concept later on. And my point is, if you heavily dope the semiconductors, they can behave like conductors, even though they are still semiconductors, but their behavior, their electrical properties are just like conductors, right? So in this case, they fall into conductors properties. So materials have loosely bound electrons, 1 or 2 in the outer shell, that can move easily under the influence of voltage to form current. So when you have just 1 or 2 electrons in the outer shell, they are relatively easier to move because they are loosely bounded to the center, right? So then they can move around and conduct electricity. So why good conduction? If you look into this overlap region, or the gap or energy gap that we're going to discuss in detail later on, there's an overlap between valence band and the conduction band. So if you remember just now, we discussed about the gap between conduction band H to valence band H for insulators, for semiconductors as well. But for this particular case, for conductors, they don't have any apparent gap between CB and VB. So they are just an overlap between both. So due to this, at least a fraction of valence electrons can move through the material and conduct electricity, right? So it's a lot easier. If you can imagine, if you want to imagine as if you are the electrons, loosely bounded electrons, and you are in the mainland of Penang, and then you have to cross to the Penang Bridge to get to the island. So the distance between is like the energy gap that you have to cross to be able to reach the conduction band, which is the Penang Island in this case. So on the other hand, if you imagine a conductor, so you can say that the island and mainland are together and there's no bridge in between, right? Or perhaps if you just put bridge in between, there's no use as well because they are together anyway, right? So that's a concept. So on the other hand, if you go for a bigger separation, like in insulators, you can imagine like your mainland and the Penang Island is far apart, perhaps through the second bridge, right? Which is way longer than the first one. So that's pretty much the analogy that you can use to understand the movement between valence band to conduction band for conduction. For semiconductors, resistivity is typically in the range of 10 to the minus 4 for heavily doped semiconductors, until 10 to the 3 ohm cm for undoped or intrinsic. Okay, I think Kwati mentioned yesterday about intrinsic, extrinsic, and then Shalini mentioned about doping as well. So you can use, we got to go this one into more details about this topic. If you can use your semiconductors in undoped condition, so that means you don't include any impurities from group 3 or group 5 into silicon, just let it be the original silicon to do the conduction. So in this case, the resistivity will be around 10 to the 3, right? On the other hand, if you dope the semiconductor, the resistivity will gradually drop depending on the doping level that you are incorporating into your silicon lattice, right? So the span or the spectrum between 10 to the 4 and 10 to the minus 4 up to 10 to the 3 can be up to 7 orders of magnitude difference. So that's the effect of doping that we're going to learn later on. So semiconducting element, in this case, silicon or germanium, if you're discussing about elementary semiconductor like silicon or germanium from group 4 as an example. So you can also have compounds like the examples that you mentioned in the chat box, like gallium arsenide, argas, indium phosphide, lead sulfide, InGaN, indium nitride. So all of them have a band gap in between, typically 1 to, it can be as low as 0.7 for germanium. Germanium is only 0.7 electron volt. So that means germanium only has 0.7 here. Silicon has 1.12, right? And if you go for bigger band gap like zinc oxide, it can be 3.3 electron volt. If you go for some other combinations, it can be cadmium telluride 1.5, perovskite can be 1.6 to 1.8, for example. So various combinations. You can also move into wide band gap like 3 point something, gallium nitride 3.4 electron volt. So they can actually be tuned. So depending on what you need, right? So later on, you're going to see in devices, certain devices need the band gap to be in the high region, like a power device, for example. You need a nitride base, like gallium nitride related materials like in the 3 point something region. And on the other hand, if you want to use for solar cell, perhaps 1.5 is the optimum in that case. So it can be different combinations for different applications, okay? So periodic table of element. So from the periodic table, you can find many different semiconductor materials or materials related to semiconductor. For example, if you, the one that you're going to use a lot here in this topic, in this course, will be silicon and germanium as the host atoms. So that means if you want to incorporate impurities, you are referring to silicon as the host atom, right? So then you put in group 5 into silicon or group 3 into silicon in order to alter the conductivity of the silicon. But you can also have some other materials as well. For example, if you look at First Solar in Kulim, fabricating a team from solar cells, they are working on cadmium combining with tellurium, and then they have cadmium telluride as solar cells, right? You can also have, well, different combination here. You can have gallium, you can go with oxygen, you can have gallium oxide, for example. You can have silicon combined with germanium as another application. Okay, you can have indium and nitrogen as indium nitride, for example. Yeah, so many different combinations depending on what you want to have eventually, right? So if you look at the definition, you can compare here in terms of the band gap or the band diagram of metal on the left, which you have an overlap between the VB and CB, right? There's no apparent forbidden gap or energy gap in between. So because they are overlapped. And then for semiconductor, it's relatively bigger if you compare to metal. You can see a clear separation. So these can vary from, say, as low as 0.7 electron volt up to the wide band gap, right? 3, 4 perhaps. And then if you move into 5 plus, you already have insulators, right? So you can see a very clear difference between all these three. And you should be able to sketch the difference between the band diagrams of metal, semiconductor, and insulator clearly, right? So make sure when you draw or you sketch, you label all the VB part, the CB part, the energy gap, the Fermi level, the central part. We're going to learn about Fermi level next, and then the electron energy on the y-axis, right? So for comparison. So the band gap of silicon or other semiconductor is small enough. For example, silicon is 1.12 electron volt. So due to this, a small amount of bias or thermal excitation or optical excitation can actually give electrons enough energy to move from the VB, valence band, the valence electron, they are originally valence electrons in the outer shell, can get them excited into the conduction band if you supply energy of more than or equal to the band gap energy. Okay, so just like if you want to cross the Penang Bridge from island to from the mainland to the island, you should have enough fuel, right? Connect kereta ke, then motor ke, you should have enough minyak kena cukup lah. Minyak kena cukup for you to cross the bridge, or else you'll be stuck in the middle, perhaps. It's just that the difference is for this particular excitation process, kalau minyak tak cukup, it won't stuck in between. It won't go at all, right? It won't just go but stop, but it won't go at all. Kalau if it's not more than or equal to EG, then it will just stay there in the valence band, not excited, right? So, right, the moment they are all excited, they are free to conduct electricity and perform the conduction. At room temperature, there are generally sufficient number of electrons in the CB to support current conduction. So at room temperature, okay, generally we have enough carriers or electrons to conduct. Okay, so I'm going to share with you on e-learn later on a video where thermal excitation is given to silicon wafer to test its conduction, right? Semiconductor, the EG is about 1.1 or 1.0 in this case, electron volt. If you talk about insulators, they are typically big, right? So we'll discuss more when we discuss the concept of band gap later on. This is just an introduction. Silicon is a group 4 element along with carbon, germanium, tin, 4 valence electrons. You've learned about this. So that means the 4 valence electrons are bonded to 4 other silicon atoms in tetrahedral arrangement, okay, just like this. So each electron is bonded to another adjacent electron from the silicon atoms, right? So this is the simple lattices with cubic unit cell, right? You have learned about FCC, BCC. I don't want to go through this. So when you use your semiconductor materials, It doesn't matter whether you're using silicon or germanium or zinc oxide or lead sulfide or indium nitride or whatever that you've mentioned now. So these semiconductor materials have their own crystallinity. Okay, crystallinity. So what is crystallinity? Crystallinity is degree of structural order in a solid. Apa maksudnya? So this means structural order here means how well the atoms are arranged in the lattice. Okay, the arrangement of atoms in the lattice. So that's called structural order in the solid. Okay, how well the atoms are arranged in the solid. In a crystal, the atoms or molecules are arranged in a regular, periodic manner. So it can be regular and periodic manner. The degree of crystallinity has a big influence on hardness, density, transparency, diffusion, and whatnot. So the crystallinity of the semiconductor materials will affect many properties. Okay, these are only a little examples, only some examples, right? There are many more examples that you can relate later on with different types of crystallinity of the semiconductor materials. The first one is called amorphous. Amorphous. Sebelum dah belajar ke crystallinity in materials? Perhaps in material science, have you learned anything on crystallinity? Anyone? Anda belajar? Have you learned anything on crystallinity at all before in any previous courses? Anda belajar? Material science perhaps? Or some other courses? Anyone? Senyap je ni. Syah Zanani. Ada belajar ke Syah Zanani sebelum ni? Have you learned anything on crystallinity at all? Can unmute yourself. Can reply in the chat box. Peswan ada belajar Peswan? Anything on crystallinity at all? Senyap juga ni. Zulaika? Safiuddin, right. Briefly learn in solid state. Okay, you learn a bit in solid state. All right, good. Patient learn some basic in 307. Okay, cool. So you learn some crystallinity basics in 307. Right, that's good. Thank you. So the first one is called amorphous. Amorphous material, if you like. So you can say whether the semiconductor material is amorphous in nature or the second one or the third one. We're going to learn later on. Amorphous is the first one, such as liquids or liquids and gases, which represent an intermediate case having order over short distances. A few atomic or molecular spacing, but not over large distances. So that means this amorphous material has no periodicity at all. Tak ada periodicity. So the arrangement of atoms, tak ada any repeating pattern at all. Periodicity, right? So there's no specific arrangement of the atoms in the lattice. It's just like berterabur, scattered. You cannot really tell a single pattern of atomic arrangement or crystalline arrangement. And therefore, they are called amorphous materials because there is no periodicity in the atom's arrangement. Right. So you can see here from the tree, the first one is amorphous. So you can see that there is no specific arrangement of atoms in the lattice, right? No recognizable long-range order to the position of an atom within the material. So there's no specific arrangement that you can tell. That's the first one. The second one is called polycrystalline. Okay, polycrystalline is the intermediate case. So yang paling berterabur ialah amorphous. Yang intermediate di tengah ialah polycrystalline, right? What is polycrystalline? You can see crystalline subsections that are disjointed by grain boundaries. So that means you can see here in this arrangement, in this material, for example, you can see that there are regions where you can see a specific crystalline arrangement, right? Crystalline atom arrangement. So you can see this this portion, for example, is in a very periodic order. So dia ada satu arrangement saja. But then on the other side, you can see the neighboring region has another arrangement. But then they are contained within a border that we call grain boundaries. Okay, dia punya border tu macam map negeri ya, you call it grain boundaries. But inside there is called a grain. And that grain has a specific arrangement of atoms, right? But together as a material, they are formed by many different grains of different crystalline orientations. And that's why we call them as polycrystalline. Okay? Polycrystalline. You can see. Tapi kalau you tengok satu je, you ambil satu ni, it is actually a single crystal. Satu crystal je, one crystalline arrangement. But that portion only. But as a material, as a semiconductor material together, that you will use in your devices or whatever, they're actually polycrystalline in nature, right? On the other hand, on the far right, you can see this crystalline arrangement, or we typically call it as single crystal. We call it single crystal. You can also call it as monocrystal or monocrystalline. Monocrystalline. So that means single lah, mono, single. So mono is characterized by atomic arrangement in an orderly three-dimensional array indefinitely. So that means if you take the material as a piece and you go under, inspection or whatever, you cannot see any grain boundaries at all. So the whole material is a single crystal material, right? So only one way of arrangement of the atoms. So that's why we call it a single crystal or monocrystalline. So the most scattered one, no crystalline arrangement at all, is amorphous. The most periodic one, the most arranged one is called a single crystal or monocrystalline, just a single crystal, there's no grain boundary at all. And the one in between where you have single crystal separated by grain boundaries is called polycrystalline. Okay? So is it clear on the crystallinity of the materials? Any question on this? All good? Cool. Right. Good. Okay, let's see now the actual materials. So if you can relate back to the amorphous, poly, and single, this is how it looks like. So if you take a wafer, for example, so this wafer on the left is a silicon wafer that we use for silicon solar cell fabrication. So it's typically 5-inch wide. The width is considered as this diagonal, 5-inch. 5-inch wide. So hujung ke hujung lah lebih kurang. So that's like 5 times 2.5 what? 12.5? Okay, it can be 5-inch, it can be 6-inch. So just an example. So if you hold a monocrystalline silicon, you should expect something like this. There is no difference in colors here and there, and there is no, there's no certain shapes that you can see with different features. The whole surface of the wafer is uniform, right? You cannot see any color difference. On the other hand, if you go for the second wafer, this is called multicrystalline or poly. Poly dengan multi sama, Typically, we call it as polycrystalline, but for solar industry, it's different because it characterizes the grains which are visible in nature, visible with naked eyes. So kalau you tengok wafer sekarang, you can see grains, right? Can you see? Can you see different colors on the wafer on the right? Clear, right? So nampak kan? You can see this one light gray sikit, this one dark gray, this one perhaps darker, something like that. So these different colors, the light, the lighter, the very dark one, is due to different reflection level. Different reflection. Kenapa dia reflect at different level? Because they are made of different grains, right? They have different grains separated by grain boundaries. Grains which give different reflection level. That's what you can see with naked eyes, right? So that wafer is called polycrystalline silicon or multicrystalline silicon. On the other hand, if you want to relate to amorphous, typically amorphous is is deposited on a foreign substrate. If you look at monocrystalline or multicrystalline, kalau you wafer ni macam ni, sekarang you tengok from the top. Tapi kalau you ambil wafer tu, you tengok from the cross section, from the side. So the thickness at least for this particular application, the thickness is about 160 micron. So that's like twice of our hair thickness, cross section. Tengok ni tepi, about twice of our hair thickness. It's very, very thin and brittle. But, so those are applicable for both, mono and poly or multi. But for amorphous silicon, the silicon or some other material which is amorphous in nature, they are usually very, very thin, less than 1 micron in thickness. Since they are very, very thin, they cannot stand on its own. Maksudnya dia, kalau you pegang kertas kan, dia pegang kertas, satu kertas, A4 paper, A4 paper, kalau pegang macam ni kan dia dah macam tu kan, dia dah flex kan. So just like your hair. So just imagine what if the thickness is very, very thin, like in the region of 500 nanometers, 800 nanometers, less than 1 micron. Obviously they cannot stand on their own, so dia tak boleh jadi rigid. So that's why they have to be deposited on foreign substrates. Foreign substrate here means it can be plastic, okay, boleh plastic. It can also be glass substrates, because these substrates need to support mechanically, need to provide mechanical strength to the film. The film itself is very, very thin. Kalau you letak film aja, tak ada supporting substrate, they will just break because it's just too thin and too brittle then, right? So what do you think? Among these three, monocrystalline or polycrystalline or multi, let's call it multi, mono or multi or amorphous, which one do you think is the best? By best here, I mean the performance-wise. What do you think would make the best crystalline semiconductor material for device operation? Any guess? You can guess here. You can unmute yourself and guess. 44. We still have a few more minutes to go. Let's have a guess. So, anyone? Ravin, would you like to guess, Ravin? Which one do you think would make the best crystalline material for device operation? Ravin, you can unmute yourself.
Mono.
Mono, right? Why do you think it's mono? Any reason? Based on what you understand so far, it's okay.
Because the arrangement in order, so that makes them strong, I guess.
Okay, cool. Okay, that makes them strong. The arrangement is order. Cool, thank you very much. Right, how about Shasha? No, Shasha? What do you think would make the best one? You can unmute yourself. You can write down as well. It's all right either way. What do you think would make the best? Mono as well. Any reason, Shasha? Agak-agak. Any other? While waiting for Shasha? Okay, let's see. Shasha commented because of the arrangement. I think, yeah, similar to Ravin. Right, okay. The answer is monocrystalline, yes. Because of the crystalline arrangement and the arrangement, which is infinite in nature, that will affect the movement of carriers that we're going to learn later on. So the way carriers move in the lattice will be affected by the crystalline arrangement. Macam for example lah, kalau you lalu Dewan exam kan, masuk Dewan exam, just imagine if the chairs and the desks are in order. Ada row, ada column, you can walk easily, right? If you imagine yourself as carriers, electrons, for example, periodic arrangement, exactly, cool. So you can walk easily between the aisles. So that means your movement, your carrier transport phenomena that we're going to learn in, I think, week 4 or so, will be very smooth. So that means you can move easily. Just imagine the very same exam hall. You masuk exam hall, meja dia berterabur, kerusi dia berterabur, and you want to get to your spot. You want to get to your desk number. Is it easier or harder to get to your desk number? Melainkan kalau you terbang, which is not possible in this case. Of course, a lot harder, right? Because you have to, find your way, at least your shortest path to get to your desk, and your desk could be anywhere because there's no order of arrangement at all, right? So in that sense, mono is the best. But the details we're going to learn later on in the course, okay? And having said that, giving the example as well as now, so you know by now that the amorphous should be the worst, isn't it? Because there's no crystalline arrangement at all. And imagine yourself as a carrier or carriers. It will be very, very terrible for you to find your way through the arrangement because there's just no arrangement, right? So that makes which one to be the most expensive based on my explanations now. What do you think? If you want to produce this crystallinity, these materials with different crystallinity, what do you think which will contribute to the most expensive crystalline arrangement in terms of the processing that you know so far? Any guess? If you run a factory, which one would be the most expensive one to produce? Come on, let's finish in a few more minutes. Najia, Nasir. Najia, which one do you think is the most expensive one? Any idea, Najia? Or Putri Nor Alia? Alia? Would you like to share what you think? Having said that, the crystalline arrangement, the best one for performance is mono. Mono, right? Yes, mono. So the hardest one to produce, hence the most expensive one to produce, is monocrystalline silicon. It's just very, very difficult to produce, and you're gonna learn this one. You're gonna learn this one in 4.7 later on in terms of how do you actually produce, how do you convert the sand from the beach, for example, or from the desert, into monocrystalline silicon wafers. It is very, very difficult. You have to go through a couple of important steps. And having said that, the cheapest one would be amorphous silicon because it's just very thin to begin with, and the deposition process is a lot easier to do. Okay, and yeah, the simplicity of the process and the volume of material that you need to be deposited on the plastic, on the glass, is a lot lower if you compare to 160 micron for the mono or multi wafers. You only need like less than 1 micron, so that's like more than 200-fold of reduction in terms of the material thickness, right? So that makes it very, very cheap. So we're just gonna stop here. Okay, let you guess here one more before we continue with impurity and doping in our next class. So this is my sample during my PhD. Okay, so you can see that this material, the gray color is the material. It's actually silicon deposited on glass substrate. Okay, glass 2 is about 3.3 mm borosilicate glass. Forget the white area because the white area is the paint that I use as a reflector in my solar cell. Forget this area. We just have a look at this area. So to relate to the crystallinity that you've learned, what do you think is the crystalline silicon material prepared on this glass? Any guesses? Okay, Fatul said thin film. Okay, thin film, but then is it amorphous or poly or mono? One of the three. Anissa said mono. Okay. Any other guesses? Last page, huh? Then we're gonna be done. Amorphous. Okay. Others? Lagi? Adli said amorphous. Anissa said mono. Perhaps another one. Anissa, would you like to share? Why do you think it's mono? Fatin said poly. Okay, all right. So we have one for each. Mono, one for amorphous, one for poly. So mono, Anissa, let's hear from you. Why do you think it's mono? Any reason? Long range arrangement. Can you see the arrangement by your naked eyes? At least from this picture. Okay. Okay, right. So you're doing the thinking, right? That's why you good luck, kan? So okay, I'll come back to you. Okay, I'll come back to you shortly, right? Okay, cool. So you said mono, and then how about Adli? Any reason why you said amorphous? Adli? Okay, Fatul Bari said, if it's mono, will it be super smooth? Okay, that depends. I'll come back to that shortly. Any reason, Adli? Looks thin. Okay. So to relate back to the previous page, right? The deposited on foreign substrate, glass or plastic, for example. Okay, that makes sense. Okay, let me ask the third ones now. Fatin Nazira, why do you think it's poly? You can unmute yourself. You can write down as well. 452. Let's finish in 2 minutes. Any reason it's poly? Okay, so you are relating to the reflections, which is uneven, so maybe due to the grains. Cool, yes. Okay, so each of you got your answers right. Okay, let me explain. The first one is Fatin got it right completely because it's actually polycrystalline silicon. Okay, this whole material is polycrystalline silicon. Let me just write down here, polycrystalline silicon. So why poly? Because you can see, just like the previous example on the wafer, right? On the multi-wafer, you can see reflections here. Here is dark gray, here is light gray, and then you can see clearly the boundaries, isn't it? So in this case, kalau macam tadi you tengok wafer tu, dia punya, nampak macam stain kan, boundaries dia. But in this case, the boundaries are elongated. So the grains are elongated. Memanjang, memanjang. Memanjang kan, horizontally, you can see on in this picture, right? Elongated grains with different reflection levels, and therefore it is polycrystalline. It is amorphous if dia ada a few conditions. For your information, just to put things into perspective, this silicon was originally deposited as amorphous silicon. Bila I buat deposition during my PhD, it was amorphous silicon. If you draw this from cross section, kalau you ambil cross section, tengok di tepi. So this is glass substrate. This is originally amorphous silicon, and the thickness is about 10 microns. So that's like 1/8 of our, or 1/10 of our hair thickness. 10 micron je. Rambut bagi 10 perhaps, assuming it's 100 micron in thickness. So originally deposited as amorphous silicon, but then because my PhD was on polycrystalline solar cells, silicon solar cell, I use laser to crystallize this amorphous silicon into polycrystalline. So laser tu dia scan macam laser beam, macam kita guna scanner 3-in-1 tu. You scan sikit kan. They scan laser beam and it melts the amorphous silicon. Dia cairkan amorphous silicon, and then after the melting, bila laser dah pass through, bila laser dah pass through, the melted amorphous silicon will recrystallize and turns into polycrystalline silicon through a process that we call crystallization process. We're going to learn that later on. But it was originally amorphous silicon, laser crystallized into polycrystalline silicon, and in each region here, as discussed in multicrystalline wafer tadi, is monocrystalline. So tadi Fatin kan? Bukan Fatin lah, yang cakap mono tadi was who said mono? Anissa, right? Anissa. It was mono because of each grain is mono. So each single grain, kalau you pick one single grain, is actually mono. It could be 100, it could be 111, and you pick this grain, it could be another 101, for example. You don't know, you have to do the characterization to know the grains. But originally, completely, as a sample, is polycrystalline silicon, originally deposited as amorphous silicon, laser crystallized to form polycrystalline, and in each grain, it is monocrystalline in nature. Okay, so that means bila you buat deposition on the glass, it doesn't necessarily have to be amorphous. Even though the previous example was amorphous, you can still get monocrystalline or polycrystalline, even though the deposition was done on plastic, on glass, depending on the processes that you use to do the fabrication. So that means knowledge yang ada ni, you can do many different things to the materials, to the substrate, in order to produce many different devices of different crystalline arrangement, different carrier transport phenomena, many different things. So now you get the basics. Then the exploratory part will be on the research lah, if you're interested on the research. And then you can do many different things with the fundamentals that you learn in physics. So that's my whole point. So we're going to stop here. We're going to continue with impurity and doping in our next class. Tomorrow, right? Tomorrow, 9 a.m. So any questions so far? So now you can appreciate the concept of crystallinity, right? And the resistivity and conductivity of the three different classes of materials, insulators, semiconductors, and conductors. Okay? So no questions? Ada? All good? Semua paham? Clear? Ada apa-apa confusion so far? Clear, very good. Right, kalau tak ada apa-apa, then I'll see you tomorrow and we'll continue with impurity and doping. Okay, kepada yang berpuasa, selamat berbuka puasa. Take care, bye-bye. Assalamualaikum.